On a clear dark night, far from city lights, you can see the Andromeda galaxy with your naked eye. It appears as a faint smear of light in the constellation Andromeda, an elongated glow about the size of 6 full moons placed side by side, though far too dim for most city dwellers to notice without knowing where to look. That faint smear of light is 2.5 million light-years away. It is the most distant object visible to the unaided human eye, and it is coming toward us, not slowly drifting in the way that most galaxies drift apart as the universe expands. Coming toward us directly, pulled by gravity, falling at approximately 110 kilometers per second. It has been falling toward the Milky Way for billions of years, and will continue to do so for billions more. In approximately 4.5 billion years, the Andromeda Galaxy and the Milky Way will collide. This is not a speculation or a possibility, it is a prediction with the confidence of an orbital calculation. Astronomers measured the direction and velocity of Andromeda's approach using the Hubble Space Telescope with enough precision to run the simulation forward in time and watch the collision unfold. What they found is a slow, majestic, multi-billion-year event that bears almost no resemblance to how collisions work in everyday experience. No explosion, no impact. The two largest galaxies in the local group interpenetrate each other, pass through, orbit each other, and eventually, after billions of years of gravitational interaction, merge into a single new galaxy. The scale of what is coming is difficult to hold in the mind. The Milky Way contains somewhere between 100 billion and 400 billion stars. Andromeda contains perhaps 1 trillion. Each of these stars is separated from its nearest neighbor by distances so vast that the chance of 2 individual stars colliding during the galactic merger is essentially 0. The galaxies are not made of solid matter in the way a stone or a planet is. They are made mostly of empty space, threaded by gravity. When 2 galaxies collide, the stars pass through each other's space like 2 swarms of bees flying through one another, without individual contact, but with profound gravitational consequences for the shape and fate of every orbit in the system. The collision will take approximately 2 billion years to complete from first contact to final coalescence. The first approach, the moment the outer edges of the 2 galaxies begin to interact, is predicted in about 4.5 billion years. That encounter will not immediately merge the 2 galaxies. Gravity will cause them to separate again after the first pass, but the second pass will come, and then another, each interaction drawing more energy from the system and tightening the eventual orbit. What emerges after all the passes are completed is a single massive elliptical galaxy. No spiral arms, no flat disk, just a vast sphere of hundreds of billions of stars orbiting a shared center of gravity. This documentary follows the complete story. We begin with what the Milky Way and Andromeda actually are, and the nature of the space between them. Then we follow the evidence that tells us the collision is coming, and when. We explore the physics of galaxy mergers, how they actually work and why they take billions of years. We ask what happens to individual stars, and specifically what happens to the Sun. We explore what the night sky will look like during the merger, the burst of new star formation the collision will trigger, and what the final merged galaxy will be. And we consider what galaxy mergers tell us about the larger story of how the universe builds its structures. The collision is already approaching. The story has already begun. The timescale of the collision, 4 to 5 billion years for the first approach, is one that resists easy comparison. 4 billion years ago, Earth did not yet exist. The solar system formed 4.6 billion years ago, meaning that the Andromeda collision will arrive in approximately the same amount of time that has elapsed since Earth formed. All of biological evolution, from the first cells to every plant and animal that has ever lived, took place in that span. The collision is therefore not a remote, almost fictional event. It is as far in the future as the origin of Earth is in the past. In that span, almost anything that we can currently imagine happening on Earth will have happened, and almost everything that happens after will be something we cannot currently imagine. Understanding the Andromeda collision requires accepting a particular kind of scale, not just spatial scale, though that is enormous, but temporal scale. The event unfolds across billions of years, from the first gravitational perturbations to the final coalescence of the galactic cores, takes perhaps 2 to 3 billion years. No civilization that exists today will observe more than a fraction of this process. What we have instead is the mathematics, the ability to trace the physics forward through time using computers and the laws of gravity, and to produce a complete picture of an event that no individual observer will ever see in full. This is one of the extraordinary things about astrophysics. It allows us to know things we can never watch. There is something particular about this event that I want to name before we go further. The Andromeda collision is one of the few events in cosmology that is both inevitable and personal. It will happen to our galaxy, to our sun, to the space around Earth, however Earth may have changed by then. Most of the universe's grand events are things that happened elsewhere or billions of years ago. Black holes merging in distant galaxies, supernovae in other arms of the Milky Way. This one is different. This is our home, our neighborhood, our future. Whatever else is true about the very long future of the solar system, this is in it. It is on the calendar, and understanding it is a form of knowing where we are headed. The Milky Way is a barred spiral galaxy approximately 100,000 light-years in diameter and roughly 10,000 light-years thick at the central bulge. It contains an estimated 200 to 400 billion stars, arranged in a flat disk with a prominent central bar and several spiral arms. Our solar system sits in the Orion Arm, about 26,000 light-years from the galactic center, not quite in the outer suburbs, but not near the center either. We orbit the galactic center once every 230 million years, at a speed of approximately 220 kilometers per second. The Sun has completed about 20 of these galactic orbits since it formed 4.6 billion years ago. At the center of the Milky Way sits Sagittarius, a star, a supermassive black hole of approximately 4 million solar masses. The galaxy's central bulge surrounds it, dense with older, cooler, redder stars. The disk contains a mix of stellar ages and types, with younger, bluer, more massive stars preferentially found in the spiral arms, where active star formation is underway. Threading through the disk is an interstellar medium of gas and dust, the raw material for future star formation. This gas makes up about 10 to 15% of the visible mass of the galaxy and is unevenly distributed, with dense molecular clouds in the spiral arms and a more diffuse warm medium between them. The Milky Way is surrounded by a halo of dark matter extending far beyond the visible disk, perhaps 300,000 light-years in radius. Dark matter, which interacts gravitationally but does not emit or absorb light, makes up the majority of the Milky Way's total mass. The total mass of the Milky Way, including this dark matter halo, is estimated at roughly 1 trillion solar masses. The visible stars and gas are a small fraction of the total. The dark matter halo shapes the orbital dynamics of stars in the outer disk, holds satellite galaxies in bound orbits, and will play a central role in the dynamics of the galactic merger when it comes. The Andromeda Galaxy, catalogued as Messier 31, is the nearest large spiral galaxy to the Milky Way. It is considerably larger, estimates of its diameter range from 140,000 to over 200,000 light-years. Its stellar mass is comparable to the Milky Way's, but it contains significantly more total mass when dark matter is included. Andromeda has a more complex structure than the Milky Way. It appears to have been involved in significant mergers with smaller galaxies in its past, which have disrupted and thickened its disk. Its central black hole, known as M31 star, has a mass estimated at 100 million solar masses, roughly 25 times more massive than Sagittarius A star. The space between the Milky Way and Andromeda is 2.5 million light-years, about 25 Milky Way diameters. This is intergalactic space, not empty in an absolute sense, since even the voids between galaxies contain a very tenuous plasma of ionized hydrogen, but effectively empty for most practical purposes. No stars fill this space. No interstellar medium links the two galaxies yet. There is just gravity, and the slow pull it exerts across 2.5 million light-years, pulling these two massive systems toward a common rendezvous. Light takes 2.5 million years to cross this gap. The light we receive from Andromeda tonight left it 2.5 million years ago, when our genus Homo was just beginning to appear on Earth. The Milky Way and Andromeda are the two dominant members of a gravitationally bound collection of galaxies, called the Local Group. The Local Group contains more than 50 galaxies in total, but the vast majority are small dwarf galaxies orbiting either the Milky Way or Andromeda. The Milky Way's satellite galaxies include the Large Magellanic Cloud, the Small Magellanic Cloud, and the Sagittarius Dwarf Galaxy, among others. Andromeda's satellites include Messier 32, Messier 110, and a much larger collection of dwarf companions. Triangulum Messier 33 is a third spiral galaxy in the Local Group, significantly smaller than either the Milky Way or Andromeda. The Local Group is itself located at the outskirts of the Virgo supercluster, a vast concentration of galaxy groups and clusters spanning roughly 110 million light-years. At larger scales still, the Virgo supercluster is part of the Laniakea supercluster, a gravitationally defined structure of approximately 500 million light-years in extent, containing the mass of 100 million billion suns. Within this enormous structure, the Local Group is a relatively isolated subunit, its internal gravitational binding strong enough to resist the general expansion of the universe that carries most galaxies away from each other. The Milky Way and Andromeda are not drifting apart as the universe expands. They are gravitationally bound and falling toward each other. This is what makes the collision inevitable. The satellite galaxies of both the Milky Way and Andromeda will participate in the merger in their own ways. Small satellites that orbit too close to either galaxy during the merger will be tidally disrupted, their stars stripped away and incorporated into the main merger. Satellites on wider orbits may survive the merger relatively intact, though their orbits around the combined system will be severely perturbed. The Large Magellanic Cloud, the Milky Way's largest satellite, is itself a substantial galaxy of perhaps 30 billion solar masses. It will likely be incorporated into the Milky Way before Andromeda arrives, in a smaller but significant merger of its own. The Sagittarius Dwarf Galaxy provides direct evidence that the Milky Way is already a serial galaxy eater. Discovered in 1994, the Sagittarius Dwarf is a small satellite galaxy currently being tidally disrupted by the Milky Way's gravity. Its stars have been stripped into a long stellar stream that wraps around the Milky Way multiple times, tracing the path of its disrupted orbit. Surveys of stellar chemistry in the Milky Way's halo show that many of the halo stars have chemical abundances consistent with having originated in dwarf satellite galaxies rather than in the main disk. The Milky Way has been absorbing smaller companions throughout its history. The Andromeda merger will be the same process, at an incomparably larger scale. The distances involved in this chapter have a particular quality that is worth dwelling on before we move to the mechanics. 2.5 million light-years. Light, the fastest thing in the universe, takes 2.5 million years to make that crossing. The most recent light from Andromeda that reaches your eyes tonight started its journey when the genus Homo was new and would not reach fully modern human form for another 2 million years. The galaxy you see in the sky is not the galaxy as it currently is, but as it was before your species existed. And the gravitational force it exerts on us, the force drawing us together, has been traveling across that gap for the entire age of the Earth. On human timescales, nothing seems to be happening. On cosmic timescales, two of the largest objects in our corner of the universe are in freefall toward each other. All of the numbers in this chapter, the diameters, the distances, the masses, have the characteristic of being so large that intuition fails to hold them. This is a routine feature of astronomy, and it is worth accepting rather than fighting. What matters is not that you can visualize 2 million light-years, but that you understand the relationship between the numbers. Andromeda is 25 galaxy diameters away. It is moving toward us at speeds that, while enormous by human standards, are small relative to that distance, and the force drawing it toward us is the same force that keeps the moon in orbit, scaled up to the mass of 1 trillion suns. Gravity at every scale follows the same rules. The same physics that governs a thrown ball governs this collision. That is both reassuring and strange. The approach of Andromeda was first confirmed through spectroscopy in the early 20th century. When light from a source moving toward an observer is analyzed through a spectrograph, its spectral lines are shifted toward shorter, bluer wavelengths, a phenomenon called blue shift. The astronomer Vesto Slipher measured the blue shift of Andromeda's light in 1912 and found it was approaching the solar system at approximately 300 kilometers per second. This was one of the largest velocities ever measured for an astronomical object at the time, and was initially puzzling. Other galaxies that Slipher measured showed redshifts. They were moving away, as the expanding universe requires. Andromeda was moving toward us. The mutual gravitational attraction of two massive galaxies was winning over cosmic expansion. The measurement of 300 kilometers per second is the radial velocity of Andromeda, its speed directly along the line of sight toward or away from us. But radial velocity alone is not sufficient to predict the collision trajectory. A galaxy moving at 300 kilometers per second along our line of sight could still miss us if it has a large transverse velocity, a sideways component of motion that would carry it past us rather than into us. For many decades after Slipher's measurement, astronomers knew that Andromeda was approaching, but could not determine whether a direct collision was certain or merely possible. Measuring the transverse velocity of a galaxy 2.5 million light-years away is extraordinarily difficult. Even at 300 kilometers per second, the apparent sideways motion of Andromeda across the sky is less than 1/1,000,000th of an arcsecond per year, far too small for ground-based telescopes to detect against the uncertainty introduced by Earth's atmosphere. The measurement required the precision of the Hubble Space Telescope and a dedicated observing campaign stretching over several years. In 2012, a team led by Roland van der Marel published a definitive proper motion measurement of Andromeda using Hubble observations separated by 5 to 7 years of baseline. The result was both precise and unambiguous. The van der Marel team's measurement of Andromeda's transverse velocity, the sideways component of its motion, found it to be much smaller than the radial velocity. The numbers meant that Andromeda was moving almost directly toward the Milky Way, not past it. The most likely scenario, based on the measured velocity components and the gravitational modeling of the two galaxies, is a nearly head-on collision with the first close approach in approximately 3.9 to 4.5 billion years. The range of uncertainty in the timing reflects uncertainties in the masses of the two galaxies and their dark matter halos, factors that affect the gravitational force each exerts on the other. The uncertainty does not extend to whether the collision happens. It does happen in every version of the simulation. The simulation itself uses a technique called n-body integration, the direct numerical computation of the gravitational forces between a large number of particles representing the stars, gas, and dark matter of each galaxy. The galaxies are each represented by tens of millions of particles, each particle contributing gravitational force to all others at each time step. Modern supercomputers can track these interactions over billions of years of simulated time in hours or days of computation. The results, published by NASA in 2012 and updated with Gaia space mission proper motion data in subsequent years, show the same basic outcome: first close passage, a partial separation, return, and final merger. The timeline has been refined, but the conclusion has not changed. The Gaia space mission, launched by the European Space Agency in 2013, measured positions and proper motions of over 1 billion stars in the Milky Way with unprecedented precision. As a byproduct, it also measured the proper motions of stars in nearby satellite galaxies and contributed improved measurements of the Andromeda system. The Gaia collaboration published refined local group dynamical modeling that placed the most likely first passage at approximately 4.5 billion years from now, with improved constraints on the mass of both galaxies. These measurements also better constrained the fate of the Triangulum galaxy, the third member of the local group, which will likely be drawn into the merger at some point in the multi-billion-year process. The confidence of the collision prediction rests on two foundations. The first is the direct observational measurement of Andromeda's velocity and direction, which modern instrumentation has now constrained to a small uncertainty. The second is the physical law governing the motion. Newton's law of gravity and Einstein's general relativity both predict the same trajectory for these masses at these separations and velocities to the precision needed for this prediction. The same physics that allows us to calculate the trajectory of a spacecraft launched from Earth and predict its position years later governs the orbit of Andromeda around the Milky Way. The physics is not uncertain. The measurement has been made. The collision is confirmed. It is worth noting what this prediction represents as a scientific achievement. Astronomers in 2012 announced with confidence an event that will occur in approximately 4 billion years. The margin of uncertainty in the timing is a few hundred million years, and uncertainty of perhaps 10% in a timescale 4 times the age of the Earth. This prediction will never be verified by any human being or any instrument we can currently conceive of. And yet it is not speculation or extrapolation. It is the application of well-understood physics to well-measured quantities. The precision of the prediction is a direct measure of the reliability of those underlying physical laws. The 2012 announcement came with a visualization produced by NASA, a computer-generated simulation showing the night sky as seen from Earth at various stages of the merger, billions of years from now. In this simulation, a faint smear of light in Andromeda becomes gradually brighter and larger over the course of billions of years, eventually filling a significant portion of the night sky during the first close approach. then taking on a distorted and extended form as tidal tails develop. The images are striking not because they are surprising, the physics behind them is well understood, but because they make viscerally real a timescale that is almost impossible to relate to human experience. Billions of years, rendered as a sequence of night sky photographs. The Gaia mission also provided independent constraints on the Milky Way's own mass, which is a critical input to the collision simulation. If the Milky Way is more massive, it exerts a stronger gravitational pull on Andromeda, and the collision happens sooner. If it is less massive, the timeline shifts. Gaia-based mass estimates for the Milky Way, combined with the proper motion measurements of Andromeda, allow the most precise timeline prediction to date. The current best estimate is a first close passage in approximately 4.5 billion years, with uncertainties of a few 100 million years in either direction. The final merger of the galactic cores is predicted to occur roughly 2 billion years after the first approach, approximately 6 to 7 billion years from now. The Andromeda collision is coming, and it is coming with a precision we can calculate. But the collision is not the end of the story. It is the beginning of a much longer process. Understanding what will actually happen when the two galaxies meet requires understanding the physics of how galaxy mergers work, which is quite different from what the word collision might suggest. That is the subject of the next chapter. When astronomers say that two galaxies will collide, they mean something very different from what the word collision implies in everyday experience. When you drop a stone on a tile floor, the stone and tile collide because their atoms cannot occupy the same space. The electromagnetic forces between electrons prevent physical overlap. This is what makes ordinary collisions brief and violent. Galaxies do not work this way. A galaxy is almost entirely empty space. The average distance between stars in the Milky Way disk is about 4 light-years, roughly the distance from the Sun to Proxima Centauri. Two galaxies passing through each other are like two almost empty spaces passing through two other almost empty spaces. The collision is violent only at the level of gravity, not of physical contact. What drives the actual dynamics of a galaxy merger is gravitational interaction between large masses over large distances. As the two galaxies approach, the tidal forces, differences in gravitational pull across the extent of each galaxy, begin to distort their shapes. Stars on the side of the Milky Way closest to Andromeda feel a stronger gravitational pull from Andromeda than stars on the far side. This differential force stretches the outer regions of each galaxy, pulling stars away from the main disk and flinging them into long curved arcs called tidal tails. Tidal tails can stretch for hundreds of thousands of light years and represent a significant fraction of a galaxy's outer stellar population being permanently rearranged. The best nearby laboratory for observing a galaxy merger in progress is the antennae galaxies, also known as NGC 4038 and NGC 4039, located approximately 45 million light-years from Earth. These two spiral galaxies are in the midst of their first close passage. Hubble images of the antennae show two bright galaxy cores still visible as separate structures, surrounded by a chaotic field of distorted star-forming regions, and two enormous tidal tails arcing outward like the antennae of an insect, which is what gave the system its name. The antennae are not a prediction of what the Milky Way and Andromeda will look like in 4 billion years. They are the same process happening now, close enough to observe in detail. The dynamical mechanism that ultimately brings the two galaxy cores together is called dynamical friction. As one galaxy passes through the other, the massive dark matter halo of each galaxy passes through the other's halo, and each mass exerts a gravitational drag on the other. This is not friction in the ordinary sense. It does not require surfaces to rub together. It arises from the fact that as a massive object moves through a distribution of other masses, it gravitationally deflects those masses slightly behind it, and their combined gravitational pull acts as a retrograde drag force, slowing the object's motion. Dynamical friction is the mechanism by which galaxies lose orbital energy during mergers and eventually spiral together. Without it, the two galaxies might simply pass through each other and continue on their way. Computer simulations of galaxy mergers universally predict a multi-pass process. After the first close approach, the two galaxies separate, drawn back together by gravity, but not yet bound into a single orbit. They recede from each other, slow, and then fall back together for a second pass. After several such encounters, each pass losing more orbital energy to dynamical friction and tidal disruption, the two galactic cores eventually approach each other in a final coalescence. The total time from first pass to final merger is typically 1 to 3 billion years. For the Milky Way and Andromeda, simulations predict the final coalescence will occur approximately 6 to 8 billion years from now, perhaps 2 billion years after the first approach. The dark matter halos of the two galaxies play a central role in the merger dynamics. The halos are much larger than the visible stellar disks and contain most of the total mass. During the merger, the dark matter halos interact gravitationally first, before the visible disks even overlap. Tidal forces between the halos begin distorting the outer edges of the stellar disks well before the first approach. The halos of the two galaxies will interpenetrate and eventually merge into a single larger halo, a process that begins early and continues throughout the entire merger sequence. By the time the stellar cores finally coalesce, the dark matter halos will have been merging for hundreds of millions of years. The energy scales of a galaxy merger are staggering. The gravitational potential energy involved in binding together two galactic systems of roughly 1 trillion solar masses each, at a separation of 2.5 million light-years, and converting that potential energy into kinetic energy, tidal distortion and heat over billions of years, dwarfs the energy output of every star in both galaxies combined over the same period. The merger does not produce a single dramatic explosion. The energy is released gradually through tidal forces, shock heating of gas, and gravitational waves from the orbiting galactic cores. But the cumulative energy is enormous. Nothing in the history of either galaxy, including any supernova or black hole merger, will be comparable in total energy release. Astronomers have observed galaxy mergers at every stage, from first contact to final coalescence to the settled elliptical galaxy that remains. The Hubble Space Telescope's image archives contain thousands of interacting galaxy pairs and merging systems. The Atlas of Peculiar Galaxies, compiled by Holt and Arp in 1966, catalogued hundreds of unusual-looking galaxies, most of which are now understood to be mergers or tidal interaction systems. What looked peculiar to Arp turned out to be perfectly predictable by the physics of gravitational interaction. Every distorted arm, every tidal tail, every brightened core is a feature that computer simulations produce naturally from the same equations of gravity that govern everyday orbital mechanics. What the simulations also show is the enormous diversity in the outcome of galaxy mergers, depending on the masses involved, the geometry of the encounter, and the gas content of the participating galaxies. Head-on collisions produce different outcomes than glancing encounters. Gas-rich mergers produce spectacular bursts of star formation that gas-poor mergers do not. The ratio of the two galaxies' masses determines whether the merger is roughly symmetric or whether the larger galaxy effectively swallows the smaller. For the Milky Way and Andromeda, the approximate mass equality and the near head-on geometry of the encounter produce one of the most dramatic types of merger, a major merger between two large spirals that will thoroughly reshape both into something new. The role of gas in galaxy mergers is qualitatively different from the role of stars. Gas is collisional. It can be shocked, heated, compressed, and radiated. When two gas-rich galaxies collide, the gas components directly interact, producing shock heating that raises the temperature of the gas to millions of degrees in some regions, while simultaneously compressing other regions below the star formation threshold. This dichotomy, some gas too hot to collapse, other gas compressed into rapid collapse, produces the complex, chaotic appearance of merging systems. The regions of intense star formation are precisely the regions where compression is dominant. The regions of hot diffuse emission are where the shock energy is highest. Both processes are happening simultaneously throughout the merger zone. The orbital mechanics of the final coalescence are still being refined as measurements of the Milky Way and Andromeda masses improve, but the qualitative outcome is robust across all simulations. Two large spiral galaxies enter, and one large elliptical galaxy exits. The spiral arms, the flat disks, the organized rotation of both galaxies, all of these features are products of the ordered angular momentum of material orbiting a single galactic center. When two galaxies merge on a nearly head-on trajectory, the angular momenta partially cancel, and the ordered rotation cannot be maintained. What remains is a system in which stars orbit in many different planes and directions. The characteristic geometry of an elliptical galaxy. The beautiful spiral structure of both the Milky Way and Andromeda will not survive the merger. The most immediate question most people ask about the Andromeda collision is whether the stars will collide. The answer is almost certainly no, and understanding why reveals something fundamental about the nature of galaxies. The average separation between stars in the Milky Way disk is approximately 4 light-years. The diameter of a typical star is about 1.5 million kilometers, 1.5 times 10 to the power of 6 kilometers. 4 light-years is about 37.8 trillion kilometers, roughly 25 million stellar diameters. To put that in physical terms, if the Sun were reduced to the size of a grain of sand, the nearest star would be about 3 kilometers away. When two such sparse distributions pass through each other, the probability of any 2 grains of sand colliding is effectively 0. A rough calculation confirms this. The Milky Way contains roughly 200 billion stars distributed across a disk of about 100,000 light-years diameter. The probability of any given star in the Milky Way having another star pass within, say, 1 light-year of it during the merger is estimated at less than 1 in a million, even accounting for the temporary concentration of stars in the merger zones. The number of actual stellar collisions that will occur during the entire Milky Way-Andromeda merger is estimated to be essentially 0, perhaps a handful involving the most densely packed regions near the galactic cores, where the stellar density is orders of magnitude higher than in the disk. But for the hundreds of billions of stars in the outer disks, the merger will be a gravitational event, not a physical one. What does happen to stars during the merger is their orbits are profoundly disrupted. A star currently in the Milky Way's disk orbits the galactic center in a nearly circular path, its orbit determined by the smooth gravitational potential of all the mass inside its orbit. During the merger, Andromeda's gravity provides an external perturbation to this potential. Stars that are weakly bound to the Milky Way, those in the outer disk, already far from the galactic center and feeling only a weak restoring force, are most susceptible to being flung outward into tidal tails or entirely ejected from the system. stars deeper in the gravitational potential well of the galactic core are more resistant to disruption and will settle into new orbits in the merged system. The stars that are ejected from the merger into intergalactic space join a population called the intracluster stellar population. Stars that belong to no single galaxy but orbit within the gravitational potential of the galaxy group as a whole. The local group already contains a diffuse halo of intergalactic stars that were ejected from previous interactions between its member galaxies. The Andromeda merger will add significantly to this population. Some of these ejected stars will orbit the local group for billions of years, eventually being captured back into the growing combined galaxy as it settles. Others may reach escape velocity and leave the local group entirely, becoming truly isolated stars in the voids between galaxy groups. Hypervelocity. Stars are a real and observed population of stars in the Milky Way that have already received large velocity kicks from gravitational interactions near the galactic center. Some are moving fast enough to eventually escape the Milky Way entirely. During the Andromeda merger, the gravitational dynamics near the merging galactic cores will be extreme. Three-body interactions, encounters involving two stars, and the supermassive black hole of one galaxy can impart enormous velocities to one of the stars, ejecting it at speeds of thousands of kilometers per second. These events will produce a population of hypervelocity stars during the merger that will escape the combined galaxy and travel through intergalactic space indefinitely. The fate of globular clusters during the merger is a subject of active research. Globular clusters are dense spherical collections of typically 100,000 to 1 million stars orbiting in the halos of both the Milky Way and Andromeda. Both galaxies contain hundreds of globular clusters. During the merger, these massive compact objects will experience strong tidal forces and may be disrupted, contributing their stars to the stellar halo of the merged galaxy. Some globular clusters may survive the merger intact and settle into orbits around the merged system. Stripped nuclei of dwarf satellite galaxies, compact stellar systems that were once the cores of larger galaxies before tidal stripping removed their outer stars, may also become part of the merged system's globular cluster population. The chemical composition of stars in the merged galaxy will reflect both progenitor galaxies. The Milky Way and Andromeda have somewhat different star formation histories and stellar population demographics. The Milky Way has a well-studied thin disk population of relatively young, metal-rich stars and a thick disk and halo population of older, more metal-poor stars. Andromeda has a similarly complex structure, but with evidence of a more active merger history. The merged galaxy will contain stars with a wider range of ages and chemical compositions than either progenitor, mixing populations that were previously separated by 2.5 million light-years. Stellar archaeologists of the far future, if they exist, will be able to read the merger history in the chemical signatures of the combined galaxy's stellar populations. The timescales over which stellar orbits are rearranged during the merger are long but finite. Stars in the outer disk will have their orbits significantly perturbed during the first passage of the two galaxies. The rearrangement will continue through subsequent passages and during the final coalescence. The process by which a collection of stars in highly eccentric, randomly oriented orbits following a merger gradually settles into a more orderly configuration through a process called violent relaxation takes approximately 1 billion years after the final coalescence. Over this period, stars lose memory of their original orbital parameters and settle into the smooth gravitational potential of the final elliptical galaxy. The settling is not gentle. Violent relaxation involves rapid fluctuations in the gravitational potential as mass is redistributed, but the end state is a smooth, well-organized galaxy. One of the most spectacular stellar effects of a major galaxy merger is the triggering of new star formation. When the gas clouds of two galaxies collide, shock waves propagate through the gas, compressing it beyond the density threshold needed for gravitational collapse. New stars ignite throughout the merger zone, producing brilliant blue-white star clusters that stand out even at the cosmological distances where we observe other merging galaxies. This starburst activity is the subject of a later chapter. The newly formed stars add another population to the already complex mix of stellar ages and types that the merger is producing. The merged galaxy will contain ancient stars that formed when the universe was young. Stars form throughout the history of both progenitor galaxies, and young stars formed in the merger itself. What emerges from all of this is a picture of a galaxy merger as an event that is simultaneously destructive and creative. It destroys the spiral structure of both progenitors and disrupts the carefully ordered orbits of hundreds of billions of stars. And it creates new patterns, new orbits, new stars, and ultimately a new galaxy whose properties will reflect the combined histories of the two it came from. The stars themselves, for the most part, survive unscathed, unchanged in their internal physics by the merger, simply relocated in space and redirected in their velocities. The merger happens to the galaxy. The stars endure. The question that most people ask when they learn about the Andromeda collision is, what happens to us? What happens to the Sun, to the Earth, to the solar system? The answer requires careful thought because the relevant timescales overlap with other processes that will also be transforming the Sun and Earth independently of the merger. The Sun is currently 4.6 billion years old, approximately halfway through its main sequence lifetime of about 10 billion years. In approximately 5 billion years, the Sun will exhaust the hydrogen in its core and begin expanding into a red giant. The first close approach of Andromeda arrives at about 4.5 billion years from now, roughly the same time the Sun begins its final expansion. The simulations of the Andromeda merger make specific predictions about the Sun's fate. In the most widely cited NASA simulations from 2012, the most likely outcome for the Sun is that it will remain gravitationally bound to the merged system, but will be moved to a significantly different orbit. In about half of the simulated encounters, the Sun is relocated to a much larger orbit within the merged system, far from the galactic core rather than at its current moderate distance of 26,000 light-years. In a smaller fraction of simulations, the Sun is flung into a very large or highly elliptical orbit that takes it deep into the stellar halo of the merged galaxy. In only a small fraction of simulations is the Sun completely ejected from the system, the probability of the Sun's original orbit being disrupted during the first close passage of the two galaxies is estimated at approximately 12%. The probability of the Sun being captured into a significantly different orbit over the full course of the multi-billion-year merger process is much higher, perhaps 50% or more. What this means is that the Sun, and with it the solar system, will very likely end up in a very different location within the merged galaxy than it currently occupies in the Milky Way. The galactic neighborhood, the distribution of nearby stars, the proximity to star-forming regions, the location relative to the galactic center, will be fundamentally different, though the solar system's internal structure will be entirely unaffected. The probability that the solar system passes within a dangerous distance of another star system during the merger is extremely small. Even in regions where stellar density is temporarily elevated during the merger, the distances between individual stars remain enormous. The Sun's Oort cloud, The diffuse shell of cometary nuclei extending to roughly 1 light-year from the Sun might be disturbed by close stellar passages, potentially sending showers of comets into the inner solar system. This phenomenon already occurs naturally as stars pass through the outer solar system on random trajectories, and merger-related close passages would increase its frequency somewhat. But the inner planets, including Earth, are gravitationally immune to any stellar encounter that does not bring another star within a fraction of a light-year, an extremely unlikely event even during the merger. The view from Earth during the merger, if Earth still exists and if something lives on it to observe the sky, will be extraordinary. As Andromeda approaches over the billions of years preceding the first encounter, it will gradually grow in angular size on the sky. By the time of the first close approach, Andromeda will be larger and brighter than any other object in the night sky, except the Moon and the Sun. Its entire disk, spanning many degrees, will be visible to the naked eye, structured with dust lanes and star-forming regions, a vast celestial object unlike anything humans have ever seen. During the most active phases of the merger, the night sky will be filled with the distorted structures of 2 merging galaxies, tidal tails spanning the sky, and bursts of bright young stars forming in the collision zones. The increase in stellar density in the merged galaxy's core region will change the background radiation environment of the solar system if the Sun ends up in a more central location. However, even in the densest regions of the merged galaxy, the distances between stars remain large enough that no individual nearby star would represent a significant radiation hazard. The concern is less about individual stars and more about the galactic core. If the Sun's orbit brings it significantly closer to the merged galactic center, where the combined supermassive black holes will be highly active, elevated energetic radiation could in principle affect planetary atmospheres over geological timescales. This remains speculative, as the orbital history of the Sun through the merger is highly uncertain. It is important to note that by the time the first close approach of Andromeda occurs, in approximately 4.5 billion years, the Earth as we know it will likely no longer be habitable regardless of the merger. The Sun increases in luminosity by approximately 10% per billion years as helium accumulates in its core. In about 1 billion years, this gradual brightening will push Earth's surface temperature past the threshold for a runaway greenhouse effect similar to what Venus experienced. The oceans will evaporate, complex life will not survive. The Earth will still exist as a planetary body, likely with a thin atmosphere of steam and carbon dioxide, but the era of complex life on Earth's surface is constrained by the Sun's own evolution, independent of the Andromeda merger. When the Sun enters its red giant phase, approximately 5 billion years from now, it will expand to perhaps 200 times its current diameter, large enough to engulf Mercury and Venus, and possibly Earth. Even if Earth's orbit is pushed outward by the mass loss as the Sun sheds its outer layers, a possibility that has been discussed in the literature, the planet will be severely modified. The red giant phase lasts about 1 billion years before the Sun sheds its outer layers entirely, leaving behind a white dwarf of approximately half its current mass, surrounded by a beautiful planetary nebula. After this transition, whatever remains of the solar system will orbit a cooling, fading stellar remnant that provides much less energy than the current Sun. The solar system will still exist physically. The Sun will simply be a different object. The merger and the Sun's evolution are therefore parallel stories playing out on overlapping timescales, and they interact. The Sun's mass loss as it evolves will affect how strongly its gravity holds onto the outer solar system. and the merger's gravitational perturbations will affect the Sun's orbit within the galaxy. The full picture of what the solar system looks like 10 billion years from now involves both processes simultaneously. What we can say with confidence is that the solar system will endure as a gravitationally bound collection of objects for many billions of years. White dwarf and planetary remnants orbiting each other in a very different location within the combined Milkomeda galaxy. The collision is not the end of our story. It is, at most, a relocation. There is something unexpectedly calming about this picture. The collision that sounds catastrophic in the title of this documentary is, for any individual gravitational system within the merging galaxies, mostly a change of address. The solar system will go on. The planets will orbit the Sun, or its remnant. The internal physics of each world will proceed according to the same laws that govern it today. The merger does not destroy the solar system. It moves it. The drama is at the galactic scale. At the planetary scale, as at the stellar scale, the merger is a gravitational event, profound in its effects on orbits and trajectories, but not on the physical integrity of the objects involved. The galaxy that will emerge from the collision of the Milky Way and Andromeda has been given an informal name, Milkomeda. It was coined in a 2007 paper by astrophysicists T.J. Cox and Abraham Loeb, who ran detailed N-body simulations of the merger. The name stuck because it captures the essential fact. This is a new object made from two familiar ones. Milkomeda will not resemble either progenitor. It will not have spiral arms, a flat disk, or a well-organized rotation. It will be an elliptical galaxy, smooth, spheroidal, predominantly made of older stars, with little gas remaining for new star formation. It will be a very different kind of galaxy from the one we currently inhabit. Elliptical galaxies form from the mergers of two or more spiral galaxies and represent the old age of galactic evolution. They contain large numbers of older, redder stars and very little cold gas or active star formation. Their stars orbit in many different planes and directions, rather than in the organized flat disk of a spiral. The smooth, featureless appearance of an elliptical galaxy reflects a state of dynamical equilibrium. Stars moving in many directions that average out to a smooth overall distribution. The process of reaching this equilibrium from the chaotic multipass merger of two spirals takes approximately 1 billion years after the final coalescence. During that settling period, Milkomeda will still show some residual asymmetry and distortion. At the center of Milkomeda will be a combined supermassive black hole, the product of a merger between Sagittarius A star and M31 star. Sagittarius A star has a mass of approximately 4 million solar masses. M31 star, Andromeda's central black hole, is estimated at 100 million solar masses. When the two galactic cores approach in the final coalescence, the two supermassive black holes will initially orbit each other at the center of the merged galaxy. The same dynamical friction that brought the galaxy cores together will cause the black hole's orbit to decay over time. They will spiral together and eventually merge, producing a gravitational wave event of extraordinary magnitude, detectable across billions of light years, in the millihertz frequency band where the planned LISA space detector operates. Before the final black hole merger and during the approach of the two cores, the available gas funneled into the galactic center will power periods of intense activity in both supermassive black holes. Active galactic nuclei, quasars, and Seyfert galaxies are powered by gas falling onto supermassive black holes, converting gravitational energy to radiation with great efficiency. The approach of the two galactic cores, each bringing with it a large reservoir of disturbed gas from the merger, will likely trigger one or more episodes of quasar-like activity at the center of the combined system. For a cosmological observer at sufficient distance, the forming Milkomeda will briefly become one of the brightest objects in the local group, powered by the accretion activity of its merging black holes. The size of Milkomeda will be considerably larger than either the Milky Way or Andromeda individually. Galaxy mergers increase both the stellar mass and the spatial extent of the merged system. Stars that were on the outer edges of both galaxies will be redistributed into a larger halo around the combined core. Tidal tails that form during the merger eventually fall back into the system, adding to the halo stellar population. The effective radius of Milkomeda, the radius within which half the stellar mass is contained, is expected to be significantly larger than for either progenitor. The total luminosity of Milkomeda will be approximately the sum of both progenitors, though somewhat reduced by stellar evolution over the billions of years the merger takes. The shape of Milkomeda will be a triaxial ellipsoid, not a perfect sphere but an egg-shaped or rugby ball-shaped distribution of stars. This triaxiality is a common feature of merger remnants and reflects the fact that the merger geometry was not perfectly symmetric. Stars from the two progenitors orbit in the triaxial potential in many directions and planes, contributing to the smooth but non-spherical appearance. The detailed shape depends sensitively on the orbital geometry of the encounter. A head-on merger produces a more spherical remnant than a glancing one. For the Milky Way and Andromeda, which are predicted to undergo a nearly but not exactly head-on collision, the remnant will be slightly triaxial. The stellar populations of Milkomeda will span an enormous range of ages. The oldest stars in both galaxies, those that formed when the universe was 1 to 2 billion years old, will still be present in Milkomeda, 12 to 14 billion years old by the time the merger completes. Stars from every era of both galaxies' histories will orbit together in the merged system with a superimposed population of stars formed in the merger starburst. This age range is a diagnostic tool. Future astronomers studying Milkomeda would be able to read the merger history in the color magnitude diagram of its stellar populations, a historical record encoded in the stars themselves. Milkomeda will contain very little cold gas after the merger. Both the Milky Way and Andromeda consume their gas reserves in the starburst triggered by the collision. Gas that is not immediately converted into stars is heated by shockwaves and feedback from newly formed massive stars and supernovae, and either blown out of the galaxy in a galactic wind, or heated to temperatures too high for star formation. Elliptical galaxies in general are gas poor and star formation quiet as a result of their merger history. Milkomeda will settle into a quiescent state, still producing the occasional new star from residual cold gas, but at a much lower rate than the Milky Way or Andromeda today. The starburst triggered by the merger will be a brief, brilliant episode in Milkomeda's long, quiet future. The satellite galaxies of both the Milky Way and Andromeda will form a new collection around Milkomeda. Some will have been incorporated into the main merger, their stars added to the halo. Others will orbit Milkomeda at large radii, their orbital planes and distances reflecting the chaotic history of the merger. The Triangulum galaxy, if it has not been incorporated into the merger itself, will likely orbit the combined system at a significant distance. Over billions of years, these satellite galaxies will continue to be slowly absorbed by tidal forces, contributing their stars to the halo population of Milkomeda, just as the Sagittarius dwarf is currently being absorbed by the Milky Way. The surface brightness profile of Milkomeda will follow the d Vaucouleur profile characteristic of elliptical galaxies, a specific mathematical relationship between radius and brightness, where the brightness falls off smoothly with distance from the center, following a fourth root law, This profile is a signature of violent relaxation, the gravitational settling process that converts the chaotic merger remnant into a smooth, well-mixed system. Measuring this profile in real elliptical galaxies and comparing it to simulated merger remnants has confirmed that present-day elliptical galaxies are consistent with being the products of ancient major mergers. Milkomeda, when it finishes settling, will look like the elliptical galaxies we observe in nearby galaxy clusters today. Featureless ovals of warm starlight, elegant in their simplicity, there is something both melancholy and magnificent about the picture of Milkomeda, two beautiful spiral galaxies, the Milky Way with its glowing arms, its young blue star clusters, its spiral pattern traced in dust and gas, Andromeda with its vast disk, its dense core, its complex history, will both cease to exist as spirals. They will be consumed by a new, larger, quieter thing. Milkomeda will be magnificent in its own way, vast, luminous, home to hundreds of billions of stars, but it will not have the organized dynamic structure of the galaxies that produced it. It will be an elderly galaxy, and the universe will be older and in many ways quieter than it is today. Among the most spectacular consequences of the Andromeda collision will be a dramatic burst of new star formation that will far exceed the current rate in either galaxy. Both the Milky Way and Andromeda contain large reserves of cold molecular gas, the raw material from which new stars form. The Milky Way contains roughly 6 billion solar masses of molecular gas, concentrated in giant molecular clouds in the spiral arms. Andromeda contains somewhat less, having already consumed much of its gas in previous episodes of star formation. When the two galaxies collide, these gas reservoirs will be compressed, shocked, and gravitationally disturbed in ways that greatly accelerate the rate at which gas collapses into new stars. The mechanism is gas-on-gas collision. Unlike the stars, which pass through each other with negligible interaction, the gas clouds of the two galaxies do collide in the physical sense. Gas can be compressed, heated, and shocked by direct encounter. When a dense molecular cloud in the Milky Way encounters a molecular cloud from Andromeda, the collision drives the gas density above the threshold for gravitational collapse. Jeans instability sets in. The compressed cloud fragments, and each fragment contracts under its own gravity, heating as it shrinks until nuclear fusion ignites and a new star is born. This process happens throughout the collision zone, producing thousands of new star clusters simultaneously. The resulting starburst, a period of star formation rate many times above the normal background level, is a well-observed phenomenon in other merging galaxy systems. Messier 82, the cigar galaxy, is the classic nearby example of a post-starburst galaxy in which a recent gravitational interaction with its companion Messier 81 has triggered a starburst rate approximately 10 times higher than typical. Hubble images of Messier 82 show a compact, chaotic interior riddled with young star clusters, with filaments of gas and dust being blown outward by the combined wind and radiation pressure of thousands of massive young stars and supernovae. The antennae galaxies, in the midst of their own merger, show hundreds of young star clusters formed in the collision zones, some containing tens of thousands of stars in a region only a few hundred light-years across. The stars that form in the Andromeda merger starburst will be drawn from the full stellar initial mass. Function, the distribution of star masses that nature produces when a molecular cloud collapses. Most of the mass will go into low-mass stars, which are faint and long-lived. But a significant fraction will produce massive stars of tens to hundreds of solar masses, which are brilliant and short-lived. These massive stars will burn through their hydrogen fuel in millions of years, end their lives in spectacular supernovae, and enrich the surrounding gas with heavy elements. The supernovae will in turn drive shockwaves through the gas, potentially triggering further star formation or, in other regions, dispersing the gas and quenching the starburst. The young massive stars formed in the merger will also affect the gas dynamics through radiation pressure and stellar winds. The intense ultraviolet radiation from a cluster of young massive stars ionizes the surrounding gas, creating a bubble of hot plasma, a so-called H2 region, the bright pink regions visible in images of star-forming galaxies. The collective radiation and wind pressure from thousands of such stars in a starburst region can drive large-scale outflows of gas, pushing material out of the galaxy at hundreds of kilometers per second. These galactic winds carry both energy and heavy elements into the surrounding intergalactic medium, enriching it with the products of stellar nucleosynthesis. The starburst both creates new stars and expels some of the gas that would otherwise form further stars. The period of most intense star formation during the Andromeda merger is predicted to last roughly 200 million to 500 million years, a long time on human scales but brief in cosmic terms. During this period, the combined galaxy will be producing new stars at a rate many times the current rate in either the Milky Way or Andromeda. New star clusters of various masses will form throughout the merger zone. Some of these clusters will be gravitationally bound and survive as globular cluster-like objects for billions of years. Others will be loosely bound and will dissolve over tens or hundreds of millions of years, their stars dispersing into the general stellar population of the merged galaxy. After the starburst phase ends, Milkomeda will enter a quieter era. Most of the cold gas available for star formation will have been either converted into stars or expelled by stellar feedback. The galaxy will transition from a blue, actively star-forming system to a red, passively evolving one. A well-established pattern observed in the color distribution of galaxies at various stages of evolution. Astronomers refer to this transition as quenching, and major mergers are one of the primary mechanisms by which large galaxies are quenched. The red elliptical galaxies that dominate the present-day universe are mostly the products of ancient major mergers, their blue star-forming spirals having been consumed in collisions. Billions of years ago, the chemical enrichment produced by the merger starburst will increase the metallicity of stars that form during and after the event. The supernovae from the massive stars formed in the starburst will enrich the surviving gas with heavy elements, and the next generation of stars born from that gas will be more metal-rich than their predecessors. This progressive enrichment is a general feature of stellar evolution in galaxies, but major merger starbursts accelerate it dramatically. Stars formed in the Andromeda merger starburst will carry the chemical signatures of both progenitor galaxies and of the supernova-enriched gas produced during the collision itself. There is one additional feature of the starburst worth noting: its temporary brilliance. During the peak star formation period, the combined Milkomeda system will be significantly more luminous than either the Milky Way or Andromeda today. Not because the merger adds energy from outside, but because the increased star formation rate means more massive stars are shining simultaneously, each contributing enormously to the total luminosity. If observed from a distant galaxy, Milkomeda at peak starburst would appear as a luminous blue, irregular system, the kind of galaxy commonly observed at intermediate cosmological distances, where the universe was younger and mergers more frequent. We would recognize it as a starburst galaxy because we have learned to read that signature from the many examples visible in the deep sky, one of the most important observational tools for studying merger-induced star formation is infrared photometry. Dust produced by the dense molecular clouds and newly formed stars absorbs the ultraviolet and optical light from young stellar populations and re-radiates it at infrared wavelengths. making starburst galaxies among the most luminous objects in the infrared sky. The Infrared Astronomical Satellite mission in 1983 discovered a population of luminous and ultraluminous infrared galaxies whose extraordinary infrared luminosities result from heavily dust-obscured starburst activity in major mergers. These systems, some with infrared luminosities exceeding 1 trillion times the Sun's, are the most extreme examples of the same process that will occur during the Andromeda merger, scaled to higher gas fractions than what the Milky Way and Andromeda currently possess. The starburst will be brief, intense, and irreversible. It will consume the gas reserves that both galaxies have been building through billions of years of slow accumulation. After it ends, Milkomeda will have a large population of new stars orbiting in its halo, a permanent record of the merger, and very little cold gas remaining. The cycle of gas in, stars out feedback loop that drives the ongoing star formation in spiral galaxies will be broken. Milkomeda will age quietly, its new stars brightening and then dimming over millions of years, its old stars cooling over billions. The firestorm will be over. What remains will be immense, old, and still. The Andromeda collision is not an exceptional event in the history of the universe. It is a routine one. Galaxy mergers have been occurring since the first galaxies formed, less than 1 billion years after the Big Bang. The universe we see today, with its large elliptical galaxies, its great clusters, its complex cosmic web of filaments and voids, is the product of billions of years of hierarchical structure formation, in which small clumps of matter merged into larger ones. Galaxies merged with galaxies, and galaxy groups merged into clusters. The Milky Way and Andromeda are simply 2 spiral galaxies, approaching the inevitable endpoint of the same process that built every large structure in the cosmos. The modern cosmological picture of structure formation begins with tiny, quantum fluctuations in the density of the early universe, amplified by inflation that seeded the later formation of structures. Dark matter, which began gravitationally collapsing before ordinary matter could, formed the first halos. Dark matter concentrations that later attracted gas, which cooled, collapsed, and formed stars. Small dark matter halos merged into larger ones, and the galaxies within them merged with each other. This hierarchical assembly process produced the diversity of galaxy sizes and morphologies we observe today. The Andromeda merger is simply the local group's contribution to this universal process, playing out close enough that we can observe it in extraordinary detail. The Milky Way itself carries the physical record of multiple past mergers. The Gaia space mission transformed our understanding of this history by providing proper motion measurements for over 1 billion stars, allowing astronomers to trace the orbits of stars in the Milky Way's halo and identify groups of stars with similar orbital properties, signatures of ancient mergers. The most dramatic discovery was the Gaia Sausage Enceladus event, approximately 8 to 10 billion years ago. The Milky Way absorbed a large galaxy, comparable in mass to the Large Magellanic Cloud, whose stars now form a large fraction of the interstellar halo. Their distinctive radial, elongated orbits in velocity space give the merger remnant its sausage-shaped appearance in phase space diagrams. The Sagittarius dwarf galaxy merger is a more recent and still ongoing process. The Sagittarius dwarf, discovered in 1994, is currently being torn apart by tidal forces as it passes through the Milky Way's disk on a polar orbit. Its stars have been dispersed into a long stellar stream that wraps around the Milky Way 3 times, detectable through the chemical signatures of its stars, which have abundances characteristic of a dwarf galaxy origin rather than the Milky Way disk. The Sagittarius stream contains roughly 100 million stars and represents one of the largest structures in the Milky Way's halo. It is the most directly observable evidence that the Milky Way is actively consuming its satellites. Beyond the Milky Way's own history, galaxy mergers are visible throughout the observable universe. The Hubble Ultra Deep Field, an image of a tiny patch of sky taken over 11 days of cumulative exposure time, contains approximately 10,000 galaxies at distances ranging from nearby to the edge of the observable universe. A significant fraction of the galaxies in the deepest part of this image, the most distant, seen when the universe was young, are irregular, disturbed, or clearly interacting. Galaxy mergers were more frequent in the early universe when galaxies were closer together and the universe was denser. The smooth, well-settled ellipticals and spirals of the nearby universe are the result of billions of years of merging and settling. The connection between galaxy mergers and quasar activity, some of the most luminous objects in the universe, is well established. Quasars are powered by gas falling onto supermassive black holes at rates far exceeding what steady-state accretion can provide. The trigger for this high accretion rate is most often a major galaxy merger, which drives large quantities of gas toward the galactic center through tidal torques. Studies of quasar-host galaxies consistently show evidence of ongoing or recent mergers. Quasars were much more common when the universe was young, between 1 and 3 billion years after the Big Bang, which corresponds to the epoch of peak galaxy merger activity. The decline of quasar activity over cosmic time tracks the decline of major galaxy mergers. What will happen to the local group and Milkomeda in the very long term? The expansion of the universe, driven by dark energy, is causing all galaxy groups and clusters beyond our local gravitational neighborhood to recede from each other at accelerating speeds. Over the next 100 billion years, all the galaxies outside the local group will have receded to beyond the cosmological horizon. They will be moving away from us faster than light can travel between us, and will effectively vanish from our observable universe. What will remain visible to any observer in Milkomeda will be only the local gravitationally bound collection, Milkomeda itself, and whatever satellite galaxies survive. The universe visible from Milkomeda will be a single galaxy in an otherwise empty sky. The Virgo cluster, the nearest large galaxy cluster at approximately 54 million light-years, exerts a gravitational pull on the local group significant enough to potentially attract us over cosmological timescales. Whether the local group will eventually merge with the Virgo cluster depends on the exact value of the dark energy density and the precise mass of the Virgo cluster, quantities that are currently uncertain. If it does, the local group would join a vast collection of thousands of galaxies in a cluster many times the size of the local group, where further mergers would produce even larger systems. If it does not, Milkomeda will be one of the most isolated galaxies in its observable universe, growing slowly more isolated as dark energy pushes the rest of the cosmos away. Galaxy mergers are also laboratories for testing cosmological models. The distribution of merger rates as a function of galaxy mass, redshift, and environment is a direct prediction of the standard lambda CDM cosmological model. The model of a universe with cold dark matter and a cosmological constant driving accelerating expansion. Comparing predicted merger rates to observed rates of interacting galaxies across cosmic time has provided important tests of this model. The qualitative agreement is good. The hierarchical assembly of structure predicted by lambda CDM matches the general pattern of observed galaxy evolution. The quantitative agreement requires ongoing refinement, particularly regarding the physics of gas, star formation, and feedback that operate within the dark matter framework. The future of gravitational wave astronomy is particularly relevant to galaxy mergers. The planned LISA mission, the Laser Interferometer Space Antenna, will be sensitive to gravitational waves in the millihertz frequency band, precisely where the inspiral of two supermassive black holes produces its strongest signal. When the merged cores of Milkomeda approach their final coalescence, billions of years from now, the inspiral of two black holes, totaling over 100 million solar masses, will produce a gravitational wave signal detectable across much of the observable universe. Any sufficiently advanced civilization in another galaxy, with instruments sensitive enough, would be able to detect the Milkomeda core merger as a gravitational wave event. We will obviously not be there to build those instruments, but the signal will go out regardless. What galaxy mergers ultimately tell us is that the universe is not a static collection of finished objects, but a dynamic, ongoing process. The galaxies we observe today are not final forms. They are snapshots in the middle of a long evolutionary sequence that began with small density fluctuations in the early universe and will end, billions of years from now, with isolated merged remnants aging quietly in an expanding, cooling, darkening cosmos. The Andromeda collision is one chapter in that sequence. Dramatic, beautiful, and in cosmic terms, entirely ordinary. Understanding it means understanding not just what will happen to our galaxy, but how the universe builds its largest structures, and what the long view of cosmic history looks like from our particular vantage point. There is a faint smear of light in tonight's sky. If you are reading this in the northern hemisphere in autumn, and if you are far enough from city lights, you can go outside and find it. It is in the constellation Andromeda, above and to the left of the great square of Pegasus. It looks like nothing in particular. A soft, slightly elongated glow that your eyes may not even focus on unless you look slightly to the side of it, the way you have to look sideways at faint things to let the more sensitive rods of your retina register them. That glow is 2 trillion stars. It is the most distant thing you will ever see with your naked eyes. And it is coming. It has been coming for billions of years. The mutual gravity of the Milky Way and Andromeda began drawing them together shortly after both galaxies formed, when the universe was only a few billion years old. At 110 kilometers per second across 2.5 million light-years of empty space, the approach is imperceptible on any human timescale. No human being who has ever lived, or who will ever live in the ordinary biological future of our species, will see any change in the position or size of Andromeda with the naked eye. The collision is happening in the sense that it is certain and the distance is decreasing, but it is happening on timescales so vast that the word happening seems almost too active. It is more like it is scheduled. What I find most striking about this particular piece of astronomy is that we know about it at all. We know the distance to Andromeda. We know its velocity. We know the result of the encounter to the level of detail of whether the Sun will be in the inner or outer regions of the merged galaxy. We built a telescope sensitive enough to measure the sideways motion of a galaxy 2.5 million light-years away, ran the equations of gravity forward 4.5 billion years, and produced a detailed picture of an event that no human being will ever observe. This is not science predicting something that will be verified next year or next century. It is science predicting something across abyssal time, out of pure confidence in the physics. And the confidence is justified. The deep time perspective that this story offers is one of the more useful things astronomy can provide to a person lying awake at night. The ordinary troubles of a human life, the things that feel urgent and large at 2 a.m, exist on timescales of hours, days, years. The Andromeda collision exists on timescales of billions of years. Holding both scales in mind simultaneously does not diminish the human scale things. It contextualizes them. Your life and what happens in it is as real and significant as anything in this documentary. But the universe also contains 2 trillion star galaxies falling toward each other across millions of light years. And the knowledge of that changes the proportions of things in a way that is, I find, genuinely restful. The Milky Way will cease to exist as a spiral galaxy in approximately 6 to 8 billion years. Its arms, which contain our solar system, and billions of other stars in the same kind of orbital dance that has persisted for 4.5 billion years, will be dispersed and replaced by something different. The beautiful face-on structure that we can appreciate in spiral galaxies we photograph. The grand design of arms and core and dust lanes is a temporary configuration, not a permanent state. It formed, it will persist for a while, and it will end. All structures in the universe are temporary in this sense. The question is only the time scale. The night sky will look different from Earth during the merger, and different again after. During the first close approach, Andromeda will be far more prominent than it is today. Spanning degrees of sky, its core brighter than any star, its spiral structure faintly visible. In the most active phases of the merger, the sky will be extraordinary. Tidal tails arcing across it, brilliant young star clusters forming in the collision zones, 2 galaxy cores approaching each other over millions of years. After the final coalescence, the night sky, if anything still lives to see it, will be dominated by the smooth glow of Milkomeda's elliptical core, brighter than the current galactic center, with no spiral arms tracing the disk. The relationship between any observer and the galaxy that contains them will be fundamentally different from our current one. The sky carries the history of what the galaxy was, the way our sky tonight carries the history of what it is now. A spiral, structured, still-forming system, billions of years into a story that has many more chapters ahead. Milkomeda will itself persist for billions of years. Its stars will age. The most massive ones formed in the merger starburst will have already exploded as supernovae during the merger itself. Medium-mass stars like the Sun will have become white dwarfs. The most common stars, the faint red dwarfs that make up 70% of all stars in the galaxy and burn their fuel so slowly they can live for trillions of years, will still be shining in Milkomeda long after the Sun's remnant has cooled. Milkomeda will be quiet and old and large, orbited by whatever remains of the satellite galaxies. Its supermassive black hole dormant at its center, long after the gas and the starburst and the drama of the merger are a memory encoded only in the chemistry of its ancient stars. And then, much further out on the timeline, Milkomeda too will end, not in a collision, but in the slow physics of quantum and thermodynamic processes. Black hole evaporation, proton decay, if protons do decay, the gradual cooling to equilibrium. The universe grows quieter as it grows older, and the galaxies that form so brilliantly in the first billion years are themselves temporary structures in a temporary cosmos. But temporary, on these scales, still means billions of years. There is time. The universe is in no hurry. It never has been. The Andromeda collision is, among other things, a story about gravity. Gravity is the weakest of the fundamental forces, far weaker than electromagnetism, weaker than the nuclear forces that hold atoms together. A small bar magnet can counteract Earth's gravity on a paperclip. The entire mass of a planet is no competition for a pocket magnet at close range. And yet gravity wins on the largest scales, because it has no negative charges to cancel it out. Every mass attracts every other mass, with no exceptions and no shielding. Over billions of years, across millions of light years, The steady accumulation of gravitational attraction between two mass concentrations of 1 trillion solar masses produces exactly what we observe, a trajectory of inexorable approach that no other force in the universe will alter. Gravity is patient in a way nothing else is. There is something in this story that connects to the experience of being alive right now, at this particular moment in cosmic time. The universe is approximately 13.8 billion years old. Galaxies began forming roughly 1 billion years after the Big Bang. The Milky Way and Andromeda are both roughly 10 billion years old, products of the universe's first great era of galaxy formation. They have orbited each other at cosmological distances for most of that time, their mutual gravity slowly drawing them together. We are living at a moment when the approach is still billions of years from completion, when the collision is future rather than past, when the Milky Way is still a spiral galaxy with its arms intact. We are alive in the brief window when this story is in its prologue. Everything that comes next, the merger, the starburst, the elliptical remnant, the long quiet of Milkomeda, is ahead. That is a remarkable position to occupy in the cosmic calendar. Go outside tonight, if you can find a dark enough patch of sky. Find Andromeda, the faint smear of light in the autumn sky. Let yourself feel the distance, 2.5 million light years, the light leaving when our genus was new on Earth. Let yourself feel the velocity, 110 kilometres per second. The approach that will eventually bring those 2 trillion stars into the gravitational embrace of our own galaxy. And then let it be large. Let it be as large as it actually is, for as long as you can hold it. The universe does not compress to a human scale for our convenience, but we can, occasionally, expand briefly to meet it. That expansion, that brief experience of actual cosmic scale from a warm animal brain on a small planet, is one of the things sleep is for. The scale settles in the quiet. Carry it with you. Sleep well.